Let's proceed. You remember, let me give you a brief reminder. We were studying the SU2 current algebra. So we had J of Z, JB of 0 is equal to K delta AB by Z square plus epsilon ABC JC by Z plus. This defined our current algebra. And in the last class, we noted that this, we recall that J of Z can be expanded as JA of JAM by Z to the power m plus 1. Okay, sum over m. This is the usual expansion of a dimension 1 operator. We reviewed in the last class that JA of 0, JB of 0 was equal to epsilon ABC, JC of 0, so that the 0 modes form are generators of the current of just ordinary SU2. And then we also did something more interesting in the last class. We defined a J tilde such that J tilde 0 was equal to, can somebody help me here, was it 2K? K minus, anyone who has notes? K minus J3 0. Okay, then J tilde plus was equal to J minus but with a 1, exactly. Yes. Yeah, and J tilde minus was equal to J plus with a minus 1. Okay, and we showed that these also formed an SU2 current algebra. SU2 algebra. Okay, then we argued, we recalled this notion of primary operators. Okay, so an operator is primary if JA on phi I is equal to TA ij phi j by Z plus dot dot dot, where TA is the representation matrix in which, for the representation in which phi transforms. Okay, and then we recalled that we looked at primary operators phi with the highest allowed value of m. Okay, so in this is a representation matrix, but of course we're doing SU2 just to keep things simple in this round. So representation matrix representations are labeled by J. J is equal to 0, half, and so on. In the representation labeled by J, the highest value of m, Jz, is also J. So we looked at phi j. We got the most severe constraints from looking at phi j. So phi was in representation J, but in general has Z component m, and we chose m equals J. Okay, and then we looked at the action of this SU2 on this thing. Okay, now even though it had a very high value of m, the highest allowed value of m, J minus annihilated it because J tilde plus annihilated it because J tilde plus, though it was a J minus, was J minus with a 1. As m was greater than 0, so it annihilates because all primary operators are annihilated by JMs with m greater than 0. Okay, and then therefore this was a highest weight state. Okay, it was a highest weight state. It had Jz equals m, but J tilde z equals k minus m. Okay, so it was a highest weight state with J tilde z equals k minus z, and so transformed in the spin k minus j representation of J tilde. Right? Okay, and then we argued that therefore J tilde minus to the power k minus j plus 1. Is that right? 2 times this and annihilated the state. Okay, so j tilde on phi jj was equal to 0. Now j tilde minus was j plus minus 1. There was no particular reason for the minus 1s to annihilate the state, you might have thought, but it does. Okay, when we started trying to deduce the consequences of this statement. Okay, so what we did was we looked at an operator, let's say phi, and then some other operators O1 to OM. We let this live at Z, we let this guy live at Z1, this guy live at Zm, and then we chose this phi to be this guy. Okay, so this was annihilated by j tilde minus to the power 2 k minus j plus 1. Okay, then we wrote down a contour integral representation of j tilde minus. Okay, we wrote down the contour integral representation for j tilde minus, which was j plus minus 1, which since this was minus 1, we had to put j plus of z by z dz. Right, that was the contour integral representation. So when we acted with this on phi, since phi was inserted at z, we call this w. We put w minus z dw, and then we put we inserted 2k minus j plus 1 factors of this contour integral, and we use the fact that once we did that, we got 0. Okay, so the correlation function is non-zero, or maybe, but once we put these contour integrals on it and do it 2 into k minus j plus 1 times, we get 0. Okay, then we unpackage this by moving the contour to surround the other guys. And you remember that if we move the contour to surround the other guy, first let's say we're surrounding the ith operator, this factor of w minus z becomes zi minus z, because we only take the residue when w hits the ith guy. Right, and this was a regular function, so the residue was regular function w equals zi, so we got zi minus z. Okay, and then the operation, the action of this, of the j plus, was just as a t plus on the ith guy, t plus in its representation, right, where we use the OP. Please.
So when we are writing this OP of this current with these primary operators,
yes,
there is this sum over j, right?
What is
Taij phi j, right? There's
yes,
sum over j.
yes.
So this j runs over like 1 to k, is that?
1 to whatever 2j plus 1. Sorry, 1 to 2j plus 1. Right, if that j is a representation, is an m label.
M label. So all these different representations will contribute.
No, all these different vectors in a given representation. Phi is a representation of its spin j.
Okay.
Now, states in spin j representation have n values running from minus j to j. That's what that I is, I and j. They're just labels for vectors in that representation. In this case, a very simple case, it's labeled just by m. Okay, so j runs over minus m to m, so 2j plus 1 values. Just representation index. This is matrix multiplication, a representation matrix multiplying a representation vector.
Okay.
Is this clear?
Okay, so this phi I is also in some representation.
Yes.
Okay.
Why did we know that? We know that the zero modes represent SU2 and that they carry zero energy. So all states at a given energy, a given delta, appear in representations of SU2. So I've chosen the basis such that this isn't represented.
Okay.
Right, so the SU2, global SU2 commutes with the Hamiltonian. So we can simultaneously diagonalize delta and this SU2. And put SU2 in representations. Clear? Okay, excellent. Okay, and then when we did that, we basically got the following sum. We got this sum over I is equal to 1 to m, then a t plus, this is t plus in the ith representation. So it's a matrix, but I'm just writing it abstractly, over z I minus z, this whole thing acting on correlator to the power whatever it is, through k minus j plus 1, acting on correlator phi O1 to OM. Each of these O's are in their own representations of SU2. I'm not denoting that in the notation, but you know it, right? That's, these T's act on those representations. And as we discussed last time, T1 only acts on phi 1, T2 only acts on phi 2, but you have to do some combinatorics to see, to make this explicit. So, please.
What will be the contour for T1, T2 acting on O1, O2?
T1, T2 acting on O1, O2. So, it will be this and this, where this was Z1 and this was Z2.
Yeah, this is T1 on O1, T2
On O2. Right? Each of these contours is deformed into a sum of contours. That sum of contours is this sum. Right? So if you only had one power, then you'll either have T1, T plus acting on O1 or T plus acting on O2. You'll never have both. But if you have two powers, you could have these terms. Okay, so let's be totally explicit. We don't need to be funny here, because this is just a multinomial. Okay? So let's say that we look at the term where m1 powers, okay, so let me be totally explicit. Okay, so we have T1 plus to the power m1, T1 2 plus to the power m2, Tn plus to the power mn. Each of these this is divided by z1 minus z to the power m1, z2 minus z to the power m2, z3 minus z to the power mn. And then we have these, so let me, just so that I don't have to keep writing it, let me call 2 into k minus j plus 1, let's call that, let's say p, just some name, let's call it q because p is a bit hard to write, so okay, let's call it q. Okay, and then we will have q factorial divided by m1 factorial, m2 factorial, mn factorial. And this summed over all m's such that sum over mi is equal to q. Okay, this acting on correlator is equal to 0. That is clear? That's what our equation gives us. Okay. Now, we can take this master equation and look at various cases. First, let me also remind you, I forgot to remind you of this. We argued from the fact that this guy kills this. Okay? From the fact that this guy kills this, it followed that that j had to be less than equal to k. Right? Because where did that argument come from? That argument came from this guy kills this, but we know what j tilde z was. J tilde z was k minus j. Okay? But that works only if this was the condition. Okay, So we already knew that this J was less than equal to K. Okay, great. So now let's go back to this. Let's first take the simplest case, namely phi equals identity. Okay, so then this correlation function, though it looked like it was a function of z, was not. It's only a function of z1 to zn. Okay, in this case, now we've got all these various z powers. Okay, now what we can do is isolate out. So this equation is true for all values of z, because we could have inserted identity anywhere, it makes no difference. So this equation is an identity that is true for all values of z, so it's a very powerful equation. Okay, so in particular what we can do is to choose the term. I want to argue that if this is true, it must be true basically term by term that this. Oh, let me tell you exactly what I want to argue. I want to argue that the term where m1 is equal to q, okay, and all the other m's are 0, that independently annihilates the correlator. Well, what is the argument for that? Well, that term comes with the following z dependence: z1 minus z the whole to the power q. Actually, in this case, q is simply yeah, 2k plus 1, 2k, yeah? Q is simply 2k plus 1. Did we get this 2's right? I hope we got the factors of 2 right. Oh, but yeah, but this is k, because k is half integer. Yeah, 2k plus 1. Yeah, my k was normalized so it was half integer. Normalized so that it was an integer would become k plus 1. Because 2k of the half integer. Yeah, so that's what Witten would have, k plus 1, right? Okay, so we get 2, yeah, right. So in this case, the simple case, q is equal to 2k plus 1. Okay, we will sometimes find it useful to call k tilde equals 2k. So k tilde is an integer. Okay, so q is equal to k tilde plus 1. Okay, great. So in this case, we have the z1 1 over the term which was t1 to the power q, t1 plus to the power q, had coefficient z1 minus z to the power q. So to isolate this out, let's just multiply by z1 minus z to the power q minus 1 and do the contour integral. That picks up precisely this term. Since it was true for all values of z, it's true for this contour integral, and so we conclude therefore that t1 plus to the power q acting on correlator O1 to On is equal to 0. Right? Where q was k tilde plus 1. All good? Okay. Now, let us remember that all j tilde minus, okay, let us remember that j tilde minus, let us remember that we had for unitary representations, okay, we had j was equal to was less than equal to k. Okay, so now suppose you were in a unitary representation and you act with T1 plus to the power K tilde plus 1, which is equal to T1 plus to the power 2K plus 1. This power is greater than equal to 2J plus 1. Because J is less than 2J is less than 2K, less than equal to 2K. Okay? Now, for every unitary representation, therefore, this is automatically 0. Because if you act on a spin J representation, any vector in the spin J representation with raising operator 2J plus 1 times, you get 0. Because if you start with the lowest weight, guys, 2J takes you to the highest weight, and the 2J plus 1 time gives you 0. Start with any other, it's even worse. Clear? And therefore, this equation is trivial if all of these operators were unitary representations, were in unitary representations. But suppose, just suppose for a moment, we were dealing with a non-unitary current algebra. We had some representations that were, we know this conflicts with unitarity, but we had some representations in which J was greater than K. Then there would be at least one state, one state in O1, for which this thing would be non-zero. Okay? But if that lowering gives you 0, that would tell you that the only way that gives you something non-zero by representation theory, that would tell you that the coefficient behind this correlator would have to be 0. Right? Because we know that the answer is 0. For unitary representations, for representations where J is less than or equal to K, that 0 is a triviality. Okay? Where it's not a triviality, we get we start with some O that is, let's say, low enough so that raising it to K plus 1 times does not kill the correlator. But the whole thing is 0. So it tells you that the coefficient behind this thing has to be 0. Okay, now you have to work a little harder because it could be that some matrix element is 0 and so on. But you do this argument carefully for every way do it for each of the O's. Okay? You just conclude that this thing is just necessarily 0. So what we've concluded is really quite remarkable. What we've concluded is that if the theory is non-unitary, then the correlation functions with even one insertion of one of these non-unitary operators, one of these operators with J greater than or equal to K, automatically vanishes. Is this clear? So suppose, it's not very different from the unitarity argument, but it's still rather remarkable. It's telling you without assuming unitarity. Here we've not assumed any unitarity because we just started with acting something on the identity operator, which was just whatever it was. Okay, we've not assumed anything, and we can get the conclusion we reach is that okay, maybe you've got some primary operators with J greater than K, but all of their correlators will vanish. So it's like they're not there. Okay, so these sometimes people call representations with J less than or equal to K integrable representations, and they call representation. I don't exactly know why. I've never understood why this name is used. There's probably some mathematics reason for it. Okay, and they call representations with J greater than K non-integrable representations. So this result is worded as the statement that correlators involving even one non-integrable representation, any number of integrable representations, always vanish.
So non-integrable ones decouple.
Decouple. And not just decouple, they even with themselves are 0. They're just totally trivial in the sense of correlation functions. Okay, so the only interesting operators in a Wess-Zumino-Witten theory, even without unitarity, are the integrable ones. Okay, there's finite number of representations with j less than or equal to k. So this is lesson number 1.
So when we take, like, let's say all the operators to be non-unitary, then this equation will just give us a, like, there will be some coefficients and it will give us some constraint equation, right?
No, I've got an equation here to start with, just with one of the operators.
So one,
Even one is non-unitary. The answer, correlate is 0.
yeah.
Okay?
Does this tell something about this tower of states? If you start from a non-unitary representation, like in unitary representations, you have this cutoff at 2k minus j, right? As we were discussing earlier. But does this also tell us something about what will happen to these tower of states if you start with a non-unitary primary state? Let's say?
Yeah.
Does this tell us something?
Good. So you're asking what happens to this j tilde, I mean this is not 0. Yeah, so it looks like j tilde, okay, is some infinite dimensional representation of SU2. You know that this j tilde SU2 for these non-unitary operators is represented infinitely because the truncation doesn't happen. Okay, some funny stuff happens. Okay, maybe there's something interesting to say to your question. I don't have anything clear to say. Yes.
So presumably this argument also works for any compact group, I guess.
Yes. Yes.
But for non-compact groups, do these non-unitary representations become important?
Okay. Good question. Good question. For non-compact groups, non-unitary representations. Yeah. As far as I know, there's no truncation in the spectrum for non-compact groups. For instance, for SU2, see these non-compact groups, yeah. First, even Lie group representation theory for non-compact groups gives you infinite dimensional representations. Now, as far as I know, there is no representation theoretic bound on these things. The example I'm best aware of is this SL2R times SL2R, ADS3 kind of non-compact group, and in that case, for every unitary representation of SL2R, there are non-trivial current algebra representations. So I think it's very different from non-compact. I won't say in general, but at least in this example. This example was studied in great detail by Maldacena and Oguri. Okay, so I think there just all of them work. Yeah, as far as I hope I'm not saying something wrong here. Certainly for compact groups, generalize is very simple. Yes.
Is there any specific reason why we are discussing about this non-unitary states? Is there any reason?
Well, first because we get this result. You know, the thing is this, that it's surprising, right? It's surprising that SU2 has an infinite number of representations, but SU2 current algebra has only a finite number of representations. Okay? So you might ask the following question. You might ask, what if I had one of these non-unitary representations, one of these infinitely more than what you're keeping, what would you get? So that's one thing to say, but there's actually another answer that is sort of important. The answer is that let's look at Chern-Simons theorem. Okay, so this is going to be an answer that's acausal, but let me give it to you. As some of you know, if you put Wilson lines on a sphere or some genus G surface in Chern-Simons theory, but let's take S2 in Chern-Simons theory, that is in one-to-one correspondence with the space of conformal blocks of Wess-Zumino theory. Okay, and this question here, if this suggests something very interesting for Chern-Simons theory. it suggests that if you put a Wilson line in any representations with j larger than k, you just get 0 intercepts. So what I'm saying is that it's good to know results without assuming unitarity. Okay, because in some contexts you're not necessarily interested in unitary theories. Actually, even on the worldsheet of the string. So even on the worldsheet of the string, the field theory that we get on the worldsheet of the string is usually not unitary, because x0 has a long sign kinetic term. It's just that the non-unitary modes are killed by the physical state condition. Okay, so if you have some results that don't necessarily assume unitarity, they're more powerful, right? Is that addressing your question?
Like the ghosts in string theory.
Ghosts, but even without the ghosts, just x0. Yeah, but you're right, the ghosts. But even the x0 part of it is not unitary. It is the wrong sign kinetic term. Okay, yeah, right, when we do BRST quantization and gauge theory, we deal at intermediate steps with non-unitary theories. So sometimes these are useful. Right? Okay, so something that follows without using unitarity, of course, is more powerful. Okay, but as Rajat indicates, okay, fine, if we already knew that we were only going to stick to unitary representations, this was a trivial equation. So let's now move on. Okay, so let us now, please.
J's themselves are not the primaries.
What do you mean J's are not primaries?
I mean, one of the O1 to ON could not have been one of these J's.
I'm assuming that O1, you're in the case that we're looking at these non-unitary guys. If we stick to these unitary guys, I'm assuming O1s and ONs are primaries. Because I assumed this when we did the OP between J and O.
Yes.
It's just 1 by z.
Yeah. Okay, but of course then once you have this relationship, what happens to the correlation functions of descendants is obtained from the primaries. So it tells you about. Okay, other questions or comments? Okay, excellent. So now let's try to get some information out of this that would be useful even when all insertions are primary. Okay, so let's consider the following case. Let's take phi of z, O1 of z1, O2 of z2, and let's suppose that this guy is in spin j, this guy is in spin j1, this guy is in spin j2. Okay, and we play the same trick as before. The advantage of being with this 3-point function, however, is that we already know beforehand the position dependence of the 3-point function. Okay, so this is some particular position dependence, z1 minus z2 to the power h1 plus h2 minus h3 and so on. Right? You know, the usual thing times a c 1, 2, 3. Now let's be a little more explicit. Let's say that we've got an M label here. Okay, we've got an M. Let me make the notation more. Let's call this 1. Let's call this 2. Let's call this 3. We've got an M1, M2, M3 label. Okay, and now what this thing does is, with various sprinklings of z1 minus z2, powers of z1 minus z2 and z1 minus z3, okay, what we get is t plus to the power m1, t plus to the power m2 acting on this c m1, m2, m3. Sorry, let me call this alpha 1, alpha 2, where alpha 1 plus alpha 2 is equal to q. Okay, and q was equal to what? So k tilde minus j? Minus j1, right? K tilde minus j1. Okay. Now, in this case, once again, because all position dependencies are so simple, we can just take this equation and examine the equation as a function of z1, z2, z3. What we get is various powers of z1 minus z2, z1 minus z3, z1, z2 minus z3. Okay, this equation has to hold for all values of z1, z2 and z3. And it's then not difficult to convince yourself that the only way that can work is if this quantity by itself vanishes independently for each value of alpha 1 and alpha 2, such that alpha 1 plus alpha 2 is q. Right? Because each of these quantities comes with different position space dependence, and it's explicit in front of your eyes. Okay, you can play tricks by isolating particular guys by doing some contour integrals or something, but it's totally obvious if you just write it out. Is this clear? So we've concluded that t plus alpha 1, t plus alpha 2 on C m1, m2, m3 is equal to 0. Okay. Now, what does this equation tell us? This is what we have to figure out. Where alpha 1 plus alpha 2 k tilde or 2k minus j1. Okay. What should I just renamed this guy J1, J2, J3, sorry, just to make it look more symmetrical. Okay, with the old notation it would be J and then there would be a J1 and J2. Sorry about that. Okay, just so that I could have an M1, M2, M3 and it looks nice. Okay. So now what we have is this relationship on Clebsch-Gordon coefficients. But Clebsch-Gordon coefficients are completely determined by group theory. So this relationship is a relationship on representations, because if I know the representations, then I know the Clebsch-Gordon coefficients. Okay? So there are two cases once again. First case is when this relationship is just trivially satisfied. Okay, so there's this times some number. So this part is group theory, and then there is some number alpha j1, j2, j3 that is part of the data of your theory. Right? Every 3-point function has an undetermined number times the structure determined by group theory. So now first question, do you get this, the Clebsch-Gordon coefficient itself automatically obeying this relationship or not? If the Clebsch-Gordon coefficient automatically obeys it because of group theory, then this is triviality, not learned anything. But if we act on the Clebsch-Gordon coefficient and get something non-zero, then that tells us that alpha j1, j2, j3 is 0. That is the interesting case. Okay? Great. So, what we want to know is when is it the case? What we want to know is when is it the case that t plus j alpha 1, t plus alpha 2 acting on this Clebsch-Gordon, t plus alpha 1, t plus alpha 2 acting on this Clebsch-Gordon give us something that is automatically 0. Okay, that's the question. This is clear, right? Okay. Now, let's see. Suppose alpha 1 was greater than or equal to 2j1 plus 1, j2 plus 1. This is acting on j2 and this was acting on j3. Right, because we started with j1 and then moved it on to j2 and j3. Okay. Suppose alpha 1 was greater than or equal to 2j2 plus 1. In this case, this would be trivial. Because any state in J2 when raised more than 2J2 plus 1 times gives you 0. Right? This is clear, right? Okay. So this guy would be a triviality if alpha 1 was greater than or equal to 2J2 plus 1. Alpha 2, let's call this alpha 2. I'm so sorry about the bad notation. Alpha 2 was greater than or equal to 2J2 plus 1. Would also be a triviality if alpha 3 was greater than or equal to 2J3 plus 1. Now, suppose suppose that Q was greater than or equal to, suppose that Q was greater than or equal to 2J2 plus 1 plus 2J3 plus 1. Then it would have to be that either alpha 1 was greater than or equal to 2, alpha 2 was greater than this, or alpha 3 was greater than this, or both. Right? In fact, we don't even need both of these plus 1s. If it was greater than this, just greater than this, that would be true. Because 2J2 times is the largest number of raisings we can act on J2. And 2J3 is the largest number of raisings we can act on J3. So if it was greater than this, so this plus 1 and greater than equal to, okay, all terms there would be, every term that appeared would kill the guy. Okay? In this case, we would get no information. Because the Clebsch-Gordons by themselves would be 0. Okay? But what was Q? Q was 2K minus J1. Minus 2J1. Excellent. Plus 1? Plus 1. Thank you. Plus 1. Okay, thank you. Therefore, this condition is the case where we have no information. Is the case where we have 2K is greater than or equal to 2J1 plus 2J2 plus 2J3. Or K is greater than or equal to J1 plus J2 plus J3. Okay? So in the case that the sum of the three J's is less than or equal to K, we have no information. The C, J1, J2, J3s can be non-zero, could be whatever they want. In the converse of this case, however, group theory does not kill C. So the coefficient must vanish. Okay? You have to do a little thinking to make sure that, yeah. But it's clear. Group theory does not kill it. It's a very explicit C, J1, J2, J3. You just find out what you get, something non-zero. So you get something that is non-zero.
These coefficients were coming because of that multinomial expansion?
Which coefficients?
These alpha J1, J2.
No, because the multinomial expansion. Yeah, exactly. Exactly. And therefore we conclude that if we have OJ1, OJ2, OJ3 and J1 plus J2 plus J3 is greater than K, then this is just equal to 0. Okay? And so
Alpha coefficient is the structure constant.
which coefficient? The C, J1, J2, J3. That alpha, yes, it's a structure constant. Okay? The 3-point function must just vanish for J1 plus J2 plus J3 greater than K. Now you might think, okay, you might think this is a bit of a triviality, right? Because maybe, but it's not at all. You can have J1 going all the way to K, J2 going all the way to K, J3 going all the way to K. So these three things, J1 plus J2 plus J3 while staying within integrable representation, could well be larger than K. But whenever this happens, the structure constant vanishes. Okay, so this gives you, actually there's this famous fusion rule of SU2. So let me remind you of the fusion rule. The fusion rule of SU2 Lie algebra is that J1 tensor J2 is equal to sum J1 minus sum over M. M is equal to J1 minus J2 to J1 plus J2. This, of course, everyone knows. Let's not call it M, let's call it J. Okay, this everyone knows. We learned this in our first quantum mechanics course. Okay, the fusion rule for Weissumino-Witten theory, for current algebra, is that this guy here is replaced by the maximum of M is equal to J1 plus minus J2 to J max of J1 plus J2 and Jk minus J1 minus J2, because whatever appears in the fusion when added to J1 plus J2 should not exceed K. Okay, so this cut off in the fusion rule. When you fuse two guys, you don't produce everything that you could have produced through group theory. There is a cutoff in this fusion rule. Okay, that is implied by this null state, the null state for J tilde minus to the power whatever. Is this clear?
But it's to be expected because we knew that in level K we can't go beyond K.
Well, we know that we can't go beyond K, that is true, but why couldn't we have had, why couldn't we have had J1, J2 and J3, let's say this is K minus 1, K minus 1, K minus 1, fusing to some small representation.
But we would have expected some truncation.
We would have expected some truncation, yes.
It won't be just simply classical.
It won't be simply classical, that's clear, because you can't go beyond K. But here, even the small guys are removed. Okay, so the details are important and interesting. Okay, is this clear? Is this clear? Now, more generally, suppose we look at, so far what have we done? We've looked at, focusing on integrable representations, we've looked to see what we get from 3-point functions. And notice that what we got from 3-point functions was, we can word it in the following language. Please.
So this means if you have correlators with greater than K insertions, because it would have been at most, each one of them can at the least be spin 1.
Great, no, because you have to do it fusion, you have to do the fusion rule. So suppose we have phi 1, phi 2 up to phi k. Okay, this guy fuses to whatever it fuses to. Then you do the fusion rule of that with phi 3. Then you do the fusion rule of that with phi 4. And you see, it's not like things add up, right? 1 plus 1 can give you a 0. So in the fusion of phi 1 and phi 2, even if 1 and 2 are quite big representations, you get a small representation. And you can keep going. So there is no bound in the number of insertions. Okay? Is this clear?
So this K greater than J1 plus J2 plus J3 is only
For 3-point functions. 3-point functions. Right. More generally, one can analyze what you get. One can analyze what you get for 4 and higher point functions. And this analysis is complicated to actually perform, okay, because you don't know the position space dependence of the correlators. Those things are whatever they are. Okay, so it's less clear what, okay, but the final answer turns out to be very satisfying, and let me tell you about it. First, before getting to that, let me say the following thing. You see, in group theory, a singlet that you form from 3 representations is a very special object. Okay? AndCijk's were singlets that you formed from J1, J2, J3. Okay? So, you might want to call, because these things are in group theory, the objects that are consistent with group invariants, namely, the answer to this quantity is invariant under group transformations. You might want to callCijk's for 3 points conformal blocks of group theory, because it obeys all the constraints that come from symmetry, which is what a conformal block is, right? Conformal block is whatever you get for the correlation function, whatever you can say from symmetry for the correlation function. Okay? Now, in SU2, 3-point conformal blocks, Lie algebra theory, theseCijk's, are trivial, you know, they're one-dimensional. Given any 3 J's, either there's a way of fusing them to a singlet or there's not, and there's a unique way. But 4-point conformal blocks are non-trivial. Suppose I take J1, J2, J3, J4. One way of getting all 4-point quote-unquote conformal blocks. I'm saying conformal blocks here, it's quote-unquote. 4-point conformal blocks are non-trivial because this is just group theory, just Lie algebra theory. I'm just using fancy words to say everything you know. Okay? 4-point conformal blocks are non-trivial. Why are they non-trivial? They're non-trivial because you can fuse J1 and J2 to give everything between J1 minus J2 and J1 plus J2. You can fuse J3 and J4 to give everything between J3 minus J4 and J3 plus J4. And then whenever you have if there are common representations between those, you can fuse those. There may be many such common representations. So you have many ways of forming singlets out of 4 operators. It's the number of common things between J1 and J2 and J1 minus J2 and J1 plus J2 and J3 minus J4 and J3 plus J4. Some of you are thinking, oh God, this number will now depend on whether I fuse 1 with 2 and 2 with 3. Oh, but it does not. You can check for yourself that this number of common guys, if you fuse 1 with 2 and 3 with 4, or 1 with 3 and 2 with 4, you get the same number of common guys. Okay? So the dimensionality of the space of SU2 Lie algebra conformal blocks is the number of ways for 4-point functions, is the number of ways of forming singlets out of 4 representations. This is non-trivial. So non-trivial means doesn't have dimensionality 1 or 0. Some non-zero. And this is true for 5-point and 6-point and 7-point. One way of thinking of all these conformal blocks is to fuse one at a time. Choose any order you want. Fuse 1 with 2. Then whatever you get with that, fuse with 3. Whatever you get with that, fuse with 4, and so on. Okay? That is something we're used to doing, or you should be used to doing in group theory. Now, what have we seen? The space of current algebra conformal blocks. Let's first look at 3-point functions. The space of current algebra conformal blocks, as far as 3-point functions go, is a subset of the space of Lie algebra conformal blocks. Because in Lie algebra, you get any 3 J1, J2, J3 that obey the triangle inequality have 1 non-trivial conformal block and others have 0. Here, not only must it obey the triangle inequality, but it must also obey this other inequality, that is J1 plus J2 plus J3 is less than k, less than equal to k. Okay? When they are equal, if you look at any given point, there is this z dependence Z1 minus Z2, Z1 minus Z3, blah, blah, blah. And then there is the group structure dependence. And the group structure dependence was just that of Lie algebra theory. So, point by point, if you look at a given point and you look at the group structure dependence, the way of fusing these representations together was exactly the same as in group theory, except that some ways that are allowed in group theory are not allowed. Okay? And so, this is said in the following language. Mathematicians love this language and Witten has adopted it, so half of the string theory community has adopted it. There are two different uses of the word conformal block for Wess-Zumino-Witten theory. The first is a local use, namely all correlators that obey the constraints we have been studying so far, these Gepner-Witten constraints. Okay. Second is a use that it not only obeys Gepner-Witten constraints but also obeys the Canesian exam-logical equation, which is an equation we will study very soon. That determines the Z dependence of the conformal block. Notice that everything we've been talking about so far has been ultra local, Z by Z. Okay, there's no condition on variation with Z in what we've been doing. That will come. Okay, but using the first terminology, namely a conformal block is just anything that ultra locally obeys our conditions and can have so far any dependence on Z. Okay, what we have seen is that our conformal blocks, CFT conformal blocks, point by point, are some subset of the space of Lie algebra conformal blocks. Okay, now with 3-point functions this subset was global, meaning it didn't matter where you were. It didn't matter which Z1, Z2, Z3 we were working, because the Z dependence is factored out easily. When we look at 4-point functions, once again we have constraints. But these constraints, and once again, at any given position, the color structure is some SU2 singlet. Just because the correlator obeys the constraints of SU2 Lie algebra representation theory. Okay? But in general, not every way of contracting indices to give you singlets is allowed in SU2 level K representation theory, because you have to obey these Gepner-Witten equations for the 4-point functions. Okay? Which subset of these things is allowed rotates as a function of Z, more precisely as a function of the cross ratio. Okay? And one way of understanding how that works is as follows. You see, in the space of conformal blocks, you can always make conformal blocks just like in representation theory by fusing. Let's say I've got J1 and J2. I fuse to give some J prime. And then that J prime fuses with J3 to give some J double prime, and so on. Now, each of these fusions are only allowed if these 3-point functions are non-zero. So you just restrict all these intermediate guys to run over those J's that have non-zero 3-point function here and here. Okay, and that, when you do that and you do that fusion, that gives you the space of all allowed blocks, and those things automatically meet the Gepner-Witten constraint for 4 and higher point functions. Okay, I haven't shown it, but it's true. So the non-trivial constraint was in 3-point function, and then fusion, you see, 4-point functions and higher determined by fusion, determined by 3-point functions. So everything that you get by fusion with allowed things is allowed. Okay, so the non-trivial constraint came from the 3-point function. Now, if you want, we can go back and answer a question that Omkar wanted to answer. One of Omkar's questions, paraphrased, is the following. Suppose I'm in SU2 level K and I have zeta insertions. Let's say I have an insertion with J1, J2, J3, any number much larger than K, if necessary. How many different conformal blocks are there? Omkar was asking whether they vanish after a certain number. We argued they don't. But if you want to consider, count the answer to this number of conformal blocks, because you can just do it by fusion. And in each step, obey the fusion rules. J1 with J2, fuse with the SU2K, and so on. Okay? There is actually a Verlinde formula for this. You remember we talked about the Verlinde formula. Verlinde formula was related the number of invariants, Nijks. Okay, counted that in terms of the S matrix. There's some generalization of this Verlinde formula to n with arbitrary number of insertions. There's a very pretty story involving this. Verlinde formula can be reinterpreted in Chern-Simons theory. It's sort of like a unitary matrix integral, but with some discretization. It's a very pretty formula. And when we talk about Chern-Simons theory, I will come back in. So we can, not only is it non-zero, we can actually count the number of conformal blocks quite efficiently. It grows. Okay, with number of insertions. Okay, excellent. I think that's all I wanted to say about these Kepner-Witten type constraints and this local notion of conformal blocks. Any questions or comments? This will be relevant for string theory and group manifolds, but it's relevant for more than that. For instance, when we look at the heterotic string, when toroidal compactification, we often get SU2 level 1 or SU2 level 2 current algebras. Did we discuss this?
What exactly?
Did we discuss current algebra from SU2 at the self-dual radius?
Yeah, we did.
R equal to root 2, there is stuff.
Yeah. And now, maybe if you go back to that discussion, you will see that what we were discussing was actually current algebra. Okay, so let me say that. Suppose you take the free boson at self-dual radius. If you go back to one of the earlier lectures, okay, you will find that we had this e to the power I, now I can't remember the numbers, maybe square root 2, x, xl, everything, holomorphic and anti-holomorphic sort of decouple. We call this j plus, we call this j minus is e to the power I minus I square root 2 x. The square root 2 may be wrong, maybe you'll have to look up your notes, and I times del x. We called this j plus, we call this j minus, and we call this jz. And we found that ja of z, jb of 0 was equal to 1 by z square. Okay, plus epsilon abc jc. So these guys, free bosons at the self-dual radius generate a level 1 current algebra. Similarly, free fermions generate a current algebra. You take n free fermions. Okay, let's say n complex free fermions. Okay, they generate a U1 current algebra. Just from, the current is just psi by psi. Yeah, the same thing that appears when we look at bosonization. So many systems, both in general physics as well as in string theory, have these current algebras in them. Group manifolds is one example. Cosets of that is one example. But very often these current algebras pop up. Okay? And so it's important to know and be conversant with them. In particular, every time we have a gauge field in space-time in string theory, the dual operator, the dual operator to that is a dimension 1 comma, let's say a 1 comma 1 operator. Let me say this more clearly. let me remind you about the vertex operators for the graviton. Okay, in the appropriate picture, vertex operator for the graviton is del x mu del bar x mu. Okay. Now, this is a nice vertex operator because it's primary and it's a 1, 1 operator. 1, 1 because x was so to speak 0 dimension and del x is 1, del bar is 1. 1, 1 operator gives you a nice vertex operator for a graviton. Suppose I want a vertex operator for a gauge theory. Okay, so say I'm doing compactification of string theory. I'm down to 4 dimensions. I've got some internal manifold, or I'm the heterotic string even 10 dimensions. Okay, I want to gauge, one of these. How do we make a vertex operator for a gauge theory? For a gauge boson? Well, a gauge boson has to have a single vector index, not 2 vector indices like this, because that's a tensor. So one way of making a gauge boson is to take del bar x mu times some other 0, 1 vertex operator. Some 0, 1 vertex operator is not made out of the x's of the non-compact direction. So it doesn't carry a vector index in the x's of the. This then will be a good vertex operator and will, because it's massless gauge boson. Massless because it's 1, 1 without an e to the pi k dot x. E to the pi k dot x will obey the k square equals 0. Because it's massless, it will also be a gauge boson. So for this reason, every time in your string world sheet theory, you have 0, 1 operator. You have a gauge boson. So the space of gauge bosons in target space is the space same as the space of currents on your world sheet, because current algebra was the algebra of 0, 1 theories. Okay, so you see from this as well that if you are interested in gauge fields in the bulk, you should be very interested in current algebras on the world sheet. Okay, it's just always true. Yes.
But can we put like 0, 1 as vertex operators in our this string world sheet on the world sheet?
You can't put 0, 1 alone, but 0, 1 with del x becomes 1, 1.
Okay.
That's why we needed the del x. Okay, so if you have 0, 1 and a del x, then you're good. Okay, this happens a lot in the heterotic theory. You get these 0, 1 operators from winding modes in this extra torus direction. Okay. It happens when you have compactive, it happens all the time. So it's very important structure, this current algebra structure. It's extremely important, in particular for string theory.
So earlier when we were discussing this at dual radius r equal to root 2, we had this current algebras popping at r equal to dual radius. We were also doing something orbifolding and something like that. Do we have something similar there also?
Do we have something similar where?
The kind of things where...
No. There, if you remember, what we did was use the fact that we had current algebra to deduce that the orbifold at square root 2 times self-dual radius is the same as, orbifold at self-dual radius is the same as circle compactification at square root 2 times self-dual radius. That was, maybe there's something more general, but that was a very particular structure. It used the fact that we had circle compactification. It was not in an abstract setting. Okay.
Here we don't have such.
We're looking more abstractly. Just look at the space of all possibilities. Okay, excellent. Any questions or comments?
Another question. So like in the case of the self-dual, when we were looking at the compact boson, we had this confirmed manifold, and at this self-dual point, we get this current algebra.
Yes.
Is there a statement something similar about confirmed manifold for 2D CFT, like
Toroidal compactification?
maybe there things have been worked out properly?
Oh, completely.
Yeah, so you have any comment that suppose I am moving on a confirmed manifold, are there tests that I can do to find whether now I have a current algebra at this point?
Okay, good question. Good question. Basically, what you do is to look for the 0, if you have the partition function, for instance, then it's clear, because you're looking for a 0, 1 operator. Just see where you get, in the partition function you get a power of q with no q bar and to the power 1. It's that, there may be other things to say. I have the feeling Sunil Mukhi has been closely looking at such things. There's more to say, But at the simplest level, just look for the partition.
And are there high dimension generalization of current algebras like in 3D or 4D?
Now when you say D, do you mean base space or target space?
I mean, I take 4D CFT.
4D CFT, no. No, there's, you see current algebra gets all its power, like Virasoro, gets all its power from being holomorphic. Okay, the new thing that we have in current algebra that was not there in Lie algebra is these JNs, and these were conserved because of holomorphicity. Because we lack holomorphicity in higher dimensions, there is no analog that I know of current algebra in higher dimensions. Both good and bad, because current algebra, as we will see, like Virasoro, stress tensors of J's are sort of determined by algebra, whereas in high dimensions stress tensors of various J's are not determined by algebra. So there's more structure. If everything is determined by symmetry, it's both nice because you can calculate it, but then also a little boring because it's unlikely to be very interesting. So there's a trade-off. Yeah. Okay. Yeah. In general, a philosophical remark. Interesting physics usually lies at the edge, where you can say something but not too much. You can solve the harmonic oscillator to death, but okay if you do. okay. And doing good physics is often knowing how to reach that edge. See, because if you're on the left of the edge, you can do it, but it's not very interesting. You're on the right of the edge, it's very interesting, but you can't do it. It's that edge that where.
Like C equal to 1, the edge, this edge side is minimal models.
Exactly. So what a great, the people who thought of these minimal models, fantastic, right? Exactly. That was really the edge. You could solve theories exactly, and they were non-trivial. That is one kind of good physics, to do things exactly. Other kind of good physics is conceptually. You can't say things exactly, but you can say something at the edge of where you can say it reliably and yet be interesting. Anyway, I'll stop philosophizing. Okay. Excellent. More questions or comments?
So here in the SU2 example, we saw that this k has to be positive because otherwise there is just j equal to 0.
Yes.
But for non-compact cases,
Non-compact cases, k can be negative. Yeah, k can be all kinds of things. Okay. Often you will see that in string theory, a non-compact CFT will come tied with a compact CFT, and that the k's are the same. Then, of course, because of but in general, non-compact spaces are much more okay. But what about compact spaces? What about other compact spaces? That we will study. There is a simple generalization of this k being an integer to all these compact spaces. We will study that, but let's first understand everything interesting in the case of SU2. Because we want to separate two things. There are the new things because we're doing current algebra, and there are new things because you're doing E8 or whatever. Now that new thing because you're doing E8 or whatever is some boring stuff, because we all understand group theory at some level. Right? Everything really new in current algebra you can see in SU2. So let's first do that and then worry about. Then worry about. Okay, great. Fine. So let's move on. I'll take maybe 10 minutes more. Yeah, I suppose. Okay. Now, so the first really important idea we've already come across, namely that there's the second SU2 that constrains current algebra in an interesting way. By the way, as somebody commented, there were many such SU2s. You could take J plus M, J minus M, but you learn nothing new from that you didn't learn from this. This was the most informative case. Okay. Now, the second really interesting thing, and this actually makes it fascinating, link between current algebra, a thing about current algebra is its relationship to Virasoro algebra. Okay, and this is what we now want to study. Okay, sticking to SU2, consider JA of Z, JA of Z, normal order. Okay, consider this normal order JA of Z, JA of Z. What do I mean by normal order? When we were studying free boson theory, we said normal order meant, removing 2-point function. I mean the same thing here. So I'll be very, very explicit. Let me write this as JA of Z plus W, JA of Z minus K by W square, limit W goes to 0. Right, sorry, and there's a delta AB. Okay, suppose I wanted to define this with B. Right, this is what I mean by JA normal order. Okay, now this operator, where when I write this A, I imply a sum over A.
Won't you have to subtract the 1 over Z similarity in that?
I'm just subtracting 2-point function. Right, nothing more. The 1 over Z singularity will show up in correlators where there is another Z, another J. Then there may be other singularities. What about things where I show up, no, I'm not subtracting anything. This is my definition. Okay.
On right hand side there is no sum over A.
What?
Right hand side there is no sum over A.
Right hand side? Sorry. Okay. Let me separate. Suppose I call this JB. Now let me study. This is no sum over A either left or right. Now let me study sum over A, JA of Z, JB of Z. Let me study this operator. What's nice about this operator? The first thing that's nice about this operator is that it's an SU2 singlet. Clearly, because it's contracted with delta AB. J rotates, the other J rotates, the way that's a singlet. Yeah, obvious, 2 vectors, dot product. Right. That's the first thing that's nice about it. The second thing that's nice about it is that at least naively, this object here appears to be a dimension 2, 0 operator, because it's the product of two 1, 0 operators. So it's SU2 singlet 2, 0 operator somehow reminds us of the stress tensor. Okay, so let's see how, to what extent this guy behaves like a stress tensor. So in order to see that, the first thing I'm going to do is the following. I'm going to study the 3-point function, and this comes back to your question. I'm going to study the 3-point function JA of Z1, JB of Z2, JC of Z3, with the view to, after looking at this 3-point function, okay, not even 3-point function, I'm just going to study this operator product. Okay, with the view to, after looking at this 3-point function, after looking at this operator product, taking Z1 to Z2 and then taking Z3 to this common value of Z. I have to first take Z1 to Z2 because that's my definition of the operator, and then set A equals B, sum and so on, and then take Z3 to Z. Okay, so what I want to do is to find this OP. I want to find this times JB of W. I want to see whether this OP is the form, has the form that a stress tensor with current OP has.
But J is not a primary operator, right?
It's not a primary under current algebra, but as we will see, it is a primary under the Virasoro algebra. It cannot be written as del Z of something else. Under Virasoro it's a primary, current algebra is not a primary. But even to make this statement, I have to show you what the relationship between Virasoro and current algebra is. This is going to be the relationship. So hang on with that question until we understand it. This is what we are discussing now, sometimes called the Sugawara construction. Okay. So what I want to do here is to compute this OP. This is what I want to compute. And it's very tempting to do the following thing. It's very tempting to say, well, this, I can compute this OP by taking the OP of this with this, plus the OP of this with this. And that's wrong. The reason that's wrong is that we are only allowed to take OPs if the two operators which we are fusing are closer together than any other inserted operator. Right? You remember when we discussed in general this state operator map in OP, if we could surround the two operators with a circle such that there are no other insertions inside the circle, but there are other insertions outside the circle, then we could replace this path integral by a series of operators. That was our derivation of the OP. Okay? But in this case, I am interested in these two Z's at the same point. So it will, no matter where we put W, we'll never be able to surround W and Z2, as let's say Z3, with a circle that does not also include Z1. Okay? So we cannot do this OP in this wrong way. Now, despite this, as you will remember, we often did something that felt like this when we were dealing with free bosons or free fermions. And the reason for that was we were just using weak contractions. Weak contraction is a theorem. We can weak contract however we want. But you shouldn't mistake that with doing an OP. Okay? So in a free theory, you can use the fact that it's free to compute something. But if all you know is the OP, you have to be careful. Is this clear? Okay? So, okay, we're getting late. Let me start off this discussion. We'll finish it next time. I'll just stop this discussion.
Use the upper definition to do the thing.
What, the upper definition? Okay, we use the upper definition, then what?
Because now this.
Yeah. So if we can say something about this in general, then we can use the upper definition. That's the strategy. We will look at these at three separated points. Use the fact that these are holomorphic functions Z1, Z2, Z3. Okay? You'll see. So let's look at that's the idea. Let me take these three at separated points. Because Z1 and Z2 are now separated, I can now ask, what is the singularity structure? I can now use the OPs between Z3 and Z1 or Z3 and Z2 to pull out all singularities in Z3. Okay, suppose I am interested in isolating any point that is singular as Z1 goes to Z3 goes to Z1 or Z3 goes to Z2. This I can easily do. Okay, so let's do it. So this product is equal to, okay, so now we took this with this, so we get delta A C K by Z13 square times JB Z2 times JB Z2 plus, let's do the second term here, epsilon A, B, C. Now I should be careful. Let's do epsilon C, A, D, J, D of Z1, and then this is Z3 minus Z1, Z31. Those are the terms that are singular when Z3 goes to Z1. And then similarly with Z3 is plus K delta BC Z32 the whole thing square plus epsilon C B M J M Z2 divided by Z32 plus non-sing as Z3 goes to either 1 or 2. Okay, so non-singular in Z3. This is clear? And separated points, this is the structure. Now that I have this, so you see, this gives me any, let's suppose we've got the following structure. We've got insertions of 1 and 2 here, 3 here, and other operators far away, separated by a bigger region. Okay. Anything that I'm going to eventually be interested in singularities when W comes to the neighborhood of either 1 or 2. If I'm away from both 1 and 2, every other term is non-singular. So this captures everything that will be of relevance to the singular OP of that boxed equation. Now that I've got this, I now take the limit 1 to 2. Okay, I now take the limit 1 to 2 and now I now take the limit 1 to 2 and very carefully expand this, keeping all terms that are of, in both of these I forgot. This guy was this, and then this had JBZ2, and this had JAZ1. Yes, and this had JAZ1. I'm sorry, I missed it. I now take the limit, because every other term, whatever it is not singular as 3 goes to either 1 or 2. These are the only terms I've got to keep track of. And I did this legally, and now after doing this fusion, I now take the limit 1 goes to 2. That is guaranteed to produce, even in the limit 1 goes to 2, all terms that were singular, if 3 came near either 1 or 2. 3 came near this thing. Is this clear? So this I will do next class. I encourage you to try this yourself. Okay. We now have to do this fusion. We have to keep things carefully, express everything in terms of this normal ordered operator, and we get something. You will see that you get the same answer as the fusion, as the OP between something like a stress tensor, and a J, once we choose a particular normalization for this. We've just written JJ. There'll be a particular normalization that comes out, and that will turn it into a stress tensor with J OP. Then we'll do the same kind of exercise with the primary operator, and we'll also do the same kind of exercise with 2 T's. Okay, and I will show you that we will get exactly the OPs of a stress tensor. Okay, with a particular central charge. You will see all this. Keep this next time. Yeah.
So this stress tensor that we are finding is in some Virasoro sense. Now,
Yes.
What do you mean by that, Virasoro sense?
Well, the stress tensor I will get. Okay, so what do I mean? I mean that all J's and all primary operators will have OPs with the thing I will construct will have the property that all J's and all primary operators will have OPs with this in exactly the same way they would with the stress tensor of a given central charge. Okay? So the result we will reach is the following. Let's suppose that we have a conformal field theory, so which has current algebra inside some larger structure. Then in that conformal field theory, the full stress tensor must take the form, this thing we'll construct, plus something else, where that something else has non-trivial, has non-singular correlators with J's and all primaries of this current algebra. Okay, so that it will be the part of the stress tensor that completely determines everything that transforms under current, this symmetry. I don't know if that was clear, but it'll hang on, see what we do, and then it'll become clear.
So the central charge that we get from this stress tensor is related to K somehow.
Exactly. Okay, in the case of SU2, it is 3K divided by K plus 2. Okay, now let's see what sense that makes. We'll derive this, but okay, but let's see what sense that makes. You remember our discussion on group manifolds? You remember that I told you that a sphere of size square root K with some 3-form flux is SU2 current algebra at level K. And you remember that when K went to infinity, the flux was really dilute and the sphere was nearly R3. So the limit K goes to infinity, the central charge had better be 3. Okay, and 3K divided by K plus 2 has this property. Now what else do we know? The other thing we know is that when K is equal to 1, a free boson and self-dual radius implements current algebra. But a free boson at SC equals 1. 3K by K plus 2 has C equals 1. So it's this nice formula that interpolates between central charge. So central charge is always less than 3. That's when it's like an R3 conformal field theory with group manifold R3. Okay, and the central charge interpolates between that 3 and 1. Okay, you will see how this works. You'll see how this works. It's actually this current algebra stuff is very beautiful. To my mind, even more beautiful than this minimal model business. Somehow it's more physical. You know, it's more to my taste. It's very beautiful stuff. Yeah. Okay.